Hello and welcome to example sheet 3, question 2. We're looking at the simple ideal Brayton cycle. Pressure ratio of 12 is given. Compressor inlet temperature of 300 K, so this is a temperature at 0.1. And turbine inlet temperature of 1000 Kelvin, so this is at 0.3. I've drawn this here. And we're asked if for a net power output of 90 megawatts. So remember, this is equal to 90 times 10 to the 3 kilojoules per second, and we're asked to find the mass flow rate if we're given an isentropic, initially for part A, isentropic compressor and isentropic turbine efficiencies of 100%. We're asked to assume constant specific heat at room temperatures, so of course we're using the equations from the data sheet. Cp is equal to 0.05 kilojoules per kg Kelvin. You won't need your property tables booklet for this, obviously. Okay, remember that power is equal to net work done per unit mass times the mass flow rate, and of course we're given the power. We need to find the net work done per unit mass, and hence we can find the mass flow rate. Okay, so we're interested in finding W net. In order to find the mass flow rate, we know that W net is equal to the work out minus the work in. Of course, the work out is equal to H3 minus H4, which, since we're using the equations to solve this, we can change this to CpT3 minus T4. Now, when the isentropic efficiency of the turbine is equal to 1, then we know T4 is equal to T4S. And similarly, now we also want to find work in, which is equal to H2 minus H1, which is equal to Cp bracket T2 minus T1. And of course, again, since N compressor is equal to 1, T2 is equal to T2S. Okay, so we need to find T4 and T2 in order to solve these equations. T1 has been given and T3 has been given, and of course we know Cp. From a data sheet for a polytropic process, so this is to find the isentropic point, T2S over T1 is equal to P2 over P1 bracket the power of N minus 1 over N. Quite simply rearranging this equation, you'll get T2S equal to, and then when you sub in the values, okay, so you'll see here that this value P2 over P1 is 12, because obviously the pressure is increasing from points 1 to 2. Later, when we look at the value of P3 over P4, we'll actually see that it's 1 over 12. Just get those pressure diagrams in your head, like I've said before, pressure against specific volume for each of the cycles, and that will help you get these in the right order. 1.4, of course, for K is from the data sheet, and you'll find T2S is equal to 610.18 Kelvin. Now think about it, we need to find T4S in order, so we use a similar technique. Of course, the equation from the data sheet is polytropic process, so we use this to locate the isentropic point. Rearranging this equation quite simply, T4S is equal to, and of course subbing in the values, and that'll give you a value of T4S equal to 491.65 Kelvin. Now you see we found these values of T4S, and so we know T4 now, and we also know T2, so we can quite simply calculate the value of Q out, the value of Q in, take these away to find Q net, and then we put Q net into here. Sorry, I mean W net, the net work done per unit mass. And we put that into this equation here, and since we know the power, we found the mass flow rate. So W out is equal to 510.89 kilojoules per kg, and W in is equal to 311.73 kilojoules per kg. So W net is therefore equal to 510.89 minus 311.73, which will give you a value of 199.16 kilojoules per kg. Then finally, using this equation here, which is the mass flow rate, which is equal to the power output, which in this particular case is 90 times 10 to the 3 kilojoules per second. Don't forget to convert these units. Note that the base unit for power and energy is actually the kilojoule, and divide that by our calculated value for W net, and that will give you a mass flow rate of 451.69 kilojoules per kg. Having found the mass flow rate for an isentropic efficiency of both the turbine and the compressor of 100% for part A, we're now asked to find the mass flow rate for an isentropic efficiency of 80% for both the turbine and the compressor. So we need to recalculate this value of W net. So W net is equal to, which is then equal to, now remember that an inefficient turbine will always produce less output, hence this term here, and an inefficient compressor requires more work input, hence this here. Yeah, so just bear this in mind when you put this equation together, and that'll help you get it in the right order. Natural check at the end is that you're going to need a higher mass flow rate coming through that engine because you were taking into account these efficiencies. So a higher mass flow rate to produce the same amount of power. So W net out is equal to 19.04 kilojoules per kg. Then calculating the mass flow rate, which is equal to power, of course, over W net out, you're going to get 90 times 10 to the 3 kilojoules second divided by 19.04 kilojoules per kg, and that's going to give you a value of 4,724.53 kilograms per second. Now this value is slightly different to the one that you'll find on the model answers. This difference on the model answers, you'll see it's 4,742. This is basically just to do with rounding. Throughout my thing I've always used two decimal places, but depending on that, you know, in this particular instance it will affect your answer. But in an exam, as long as you're consistent, it shouldn't be a problem. Now, the most important thing to note here, though, is to look at this particular mass flow rate and what we calculated for an isentropic process. And what you'll see is that almost 10 times more mass is required through the engine to produce the power output. So it's quite significant. One thing to recommend is that you give this question another go, and you have a go using the tables as opposed to the constant CP equations. The method for this is very similar to the method we used for question 1, so you can always check that up to look at how you do it with the tables. So of course this arrangement using this equation is the quickest way to solve this particular problem, especially since you've already calculated the isentropic values to begin with. When I originally solved this, I used the equations given in the data sheet to find the values of T2A and T4A, and I found them here, and then I plugged them into the equation for W net, which is shown there, which gave me a value of 19.04 kilojoules per kg and 4W net, and then I plugged this into the equation and I found a value of 475.74. Again, due to rounding, that's why you see that slight variation. I just wanted to show you that in case any of you had tried that method originally, but I'd recommend you use this equation here because it's faster.